Good day. My name is Szymon Buhajczuk, and today I'm going to be demonstrating optical part design using Ansys SPEOS. We're going to be talking about dashboard lights. So specifically, what we'd like to do is take an LED light and somehow take that light to illuminate elements on a dashboard such as buttons, dials, and so on. But how do we do this? Well, the way it's done is through something called a light guide. A light guide takes light from one area and essentially pipes it to another, distributing the light, and it can illuminate either a single component or multiple components. When we do this sort of thing, we have a few questions we need answered. Will the lighting be bright enough? Will it be even? And finally, will visual artifacts be present when we're actually looking at our dials and buttons and so on? So what is Ansys SPEOS? Ansys SPEOS predicts the illumination and optical performance of systems. It's used in applications such as optical part design, heads-up display design and analysis, optical sensor testing, manufacturing variation simulations, far infrared simulations, and many, many more. So this Ansys SPEOS demonstration will focus on a few things. First, it's going to show you the process of initial design and analysis on an optical component, in this case, the light guide that we're going to be designing. Then we're going to look at the commonality of design tools in the Ansys ecosystem. So specifically, you're going to see how Ansys SPEOS is similar to other tools such as Ansys SpaceClaim so that you can leverage knowledge your engineers may already have to learn SPEOS in a timely fashion. Finally, we're going to look at getting quick feedback by iterating on the design, by changing small things and seeing how they affect the final output. So we're going to take this sort of design and we're going to see how it's going to look. We're going to take some measurements and we'll make informed decisions on the optical performance of the system. Let's get started. To begin, first I'd like to go and do a high-level overview of the process we'll be following throughout this demo. What you see in front of you is the Ansys SPEOS interface. We begin by importing the trim into the software. We'll then design our light guide and create a surface on which we can define the LED emitter. To do the actual simulation, we're going to jump into the light simulation tools accessible through the tab at the top of the ribbon. We're then going to switch to the simulation tree to be able to see all the tools and other objects that we define. First, we're going to start by defining an LED emitter, which you can see the rays over here. We're going to create a sensor. The sensor will allow us to see our result, have a visual representation, and take measurements as needed. We're then going to solve. And once solved, we're going to see this visual representation. And this representation can then be measured and analyzed in other ways. Another thing you'll notice is the commonality of this interface with some of the other Ansys tools you may be familiar with if you've ever worked with Ansys SpaceClaim. You'll see that actually a lot of the geometry tools are essentially the same, and this greatly reduces the learning curve for anybody that has used Ansys previously. Okay, let's start from scratch and do a deeper dive. Okay, to begin an analysis, we're going to start by importing the dash component. Once we've imported, let's start drawing a basic light guide. I'm going to go into the cross-section view, zoom in a little bit, and draw a cross-section, roughly 2 by 2 millimeters. Then we go back to the 3D view, and we pull this in both directions, 24 millimeters. Once we have our basic shape, let's draw some of the more fun indicator lights. I'm going to start by drawing a rectangle shape, a circular shape, and just for fun, let's do a squiggly. Let's finish this up. Now this could really be anything like your parking indicator, seatbelt indicator on a dash, any shape you want. I'm just keeping them simple for now. Let's go back to the 3D view and give these a little bit of depth. There we go. Now at this point, let's bring in back our dashboard again and trim off the excess. To trim off the excess material, we're going to use the split body tool, use this surface as our cutter, and remove all the extra pieces. Now we can cut out the holes for the light guide component that are little indicators by selecting our dash, using our light guide as a cutter, and let's cut out the holes. Now if I hide the light guide, you can see we have our holes. At this point, what I'm going to do is actually give these a bit of a chamfer. So let's use the pull tool with the chamfer option, and let's pull this some reasonable amount there. Now, as far as the light guide goes, let's change its color so it's more easily recognizable. I'm going to select it, display, color, white. Okay. Let's reorganize our structure tree just a little bit. I'm going to move this dash component over here and delete this. I'm going to rename this dash. I'm going to rename this light guide. Let's now create the geometry for our LED emitter. I'm going to copy, Control-C, Control-V this surface. I'm going to offset it by a certain amount and shrink it by a certain amount. I'm going to call this my LED emitter. One last thing I'm going to do is create an eye target for our sensor, which I'm going to place right here. So really, I'm just creating a coordinate system that I can point to. I'm going to rename it target. Okay. At this stage, we've completed the geometry and we're ready to jump into the light simulation tools. Okay, to get into the light simulation tools, we go to the light simulation tab, switch to simulation tree. And the first thing we're going to want to do is define a couple of materials. I'm going to first start with my plastic material. And then I'm going to create my trim material. Okay. Now, the trim is going to be assigned to the trim, and I'm actually going to assign it to the LED emitter. The LED emitter doesn't need a material, but we want to make this complete. And then the plastic will be assigned to our light guide. Okay, now that we've assigned it, let's create the materials. The first thing we'll want to do is create the surface of our trim. Okay, we're going to open up a editor called Simple Scattering Surface. You can see reflection is good. We want transmission off. The rest will keep essentially the same, and I'm going to call it rough opaque. Now that we've completed it, we can do a quick inspection of how it behaves. You can see how the incident ray is going to have a Gaussian and Lambertian kind of combination distribution as the light bounces off the surface, and there's directionality and everything considered. Okay. At this point, I'm going to jump in and create our transparent material, surface material. So I'm going to save this material, and I'm going to call it rough opaque, and I create a new one. The new one's going to be called rough transparent. And for the rough transparent one, I'm going to enable transmission. I'm going to allow 50% reflection, 50% transmission, but I could also base it on Fresnel coefficients as well, and which is calculated from the index of refraction. Okay. I'm going to just give it some parameters. I'm essentially going to make it 100% Gaussian distribution. And I'm going to save this material as my rough transparent. The next thing I want to define the volume properties of our clear plastic. To do that, I'm going to go again into our editors and create a user material. I'm going to call this high refractive index material. And I'm going to bump up the index of refraction to 2 across the entire spectrum. I could give it a distribution as a function of wavelength as well. I'm not going to do that for this demo though. I'm also going to create some scattering properties. So once this scattering function is enabled, I'm going to give the scattering behavior a little bit of directionality. So I'm going to modify the amount of scattering in different directions, angular directions. There we go. And you can see how when a ray comes in, it's going to behave in different ways in different directions. So we can preview that right here. I'm going to save this as our high refractive index material. Okay, so I think we're done defining our materials. So we're going to go back and assign them to our materials. For our plastic, for the volume, I'm going to select library, and I'm going to select our material we just created. And for the surface, instead of a mirror finish, I'm going to select library. And again, I'm going to select transparent rough as our surface material. For the trim, I'm just going to do the same, select library, and the trim is our rough opaque which we had just created. Okay, our materials are defined. Let's now create our source. Okay, our source is going to be an LED emitter, so I'm going to go to the surface source, and I will now point it to the surface we had created and accept that. You can see our rays bouncing around, or rather emitting in all directions, but they're going in the wrong direction. So I'm going to reverse this. Okay, once it's reversed, I'm going to just shorten these rays because they're a little long. This is just for visual representation so that we can see what they're doing. Okay, I think we're good now. So let's define our LED properties. We want something around 6 lumens. That's probably good. Okay. We also want to maybe reduce the angle on which it's emitted, so maybe 60 degrees would be good. And last but not least, we need some sort of light characteristics. So the spectrum that's going to emit, it's by default doing monochromatic at 555 nanometers. But what I'm actually going to do is I'm going to import an LED spectrum. Now, let me show you what this LED spectrum is. So if I open that file up, you can see that we have sort of brightness as a function of our wavelength, which is actually a much better characterization than simply just giving it a black body, for example, emission or anything like that. All right, so we've applied this profile to the LED. And once our LED is defined, let's define our sensor. Our sensor is going to be a radiant sensor. Okay, if you can see, there we go, it's popped into existence, but we're going to change some settings. First, we'll change the sensor to be a colorimetric sensor so we can actually see the colors and we can measure them and so on. Okay. We're going to now point it out at our target, which we had created. So I'm going to select our target. Okay. And I'm going to make sure that it's not reversed. And I'm going to shrink it also, just to make sure that we're not trying to capture rays from too large of an area. So as you can see, I've just brought down the range that the sensor is effective on. And let's have a look to see how that looks. Well, maybe I'll want to move things over a bit. Again, there we go. Okay, I think this is good. All right, so the range of our sensor is defined. Now we need to specify the resolution of our sensor. Right now, by default, it's 100 by 100 sampling points. I'm going to actually change this to be 500 by 500, so we get a slightly better resolution. Okay, so we have a higher resolution. We also want to do the same thing on our wavelengths. So we want 40 samples across our visual spectrum, and our sensor is defined. Now we need to select what kind of solver we want. I'm going to select my direct solver, and we're going to give it some settings. Okay, so first, we're going to want to select the geometry that's going to be simulated, which is our light guide and our trim. We're going to select our sensor, or our emitter, and now our sensor. Okay, and once we have that, I'm going to want to specify how many rays I want to collect at the sensor. Okay, a good value for this demo is 2E7. Okay, and one other thing I want to do is I want to enable something called Light Expert, which is going to allow us to troubleshoot any problems we have with our design. So I turn on Light Expert, and I enable Light Expert, LXP for short, for our radiance sensor. At this point, we hit compute. All right, so the solution is about to be completed. This only actually took a few minutes. And the more rays you have, the longer it takes, but we can get a rough estimate with fewer rays and a more detailed estimate with more rays. Okay, you can see a preview appears in our 3D display of what this looks like. I can get a more detailed display by double-clicking on the XMP in the tree. Okay, so let's take a couple of measurements, or make a few observations first. First, we can notice that there is a bit of a change in brightness as it goes along. Our circle's the brightest, our squiggle's less bright. This is something we might want to fix at some point. But I'm actually more interested in getting the raw values for it. So why don't we create a measurement of this? We do it by enabling this tool and creating a rectangle, and then doing the same, but we're going to create, there we go. We're going to create another area, except we're going to turn this into a circle using the ellipse tool. We'll move this over here. And setting our measurements to be averages. And you'll notice that the average on the rectangle is about half of the average on the circle. So that tells us that there's actually half the brightness on one than the other. We could also do a visual representation, or not visual, but a more precise visualization of the intensity of light by switching it to black to white. And you can see how lighter components appear in different colors. So it's not just the actual, what the eye would see. Okay. So we've identified now that there's a difference in brightness, but what I'm actually even more interested in is this weird glow that we're getting around all our objects. To troubleshoot this glow, what I'm actually going to do is open up Light Expert. Light Expert is going to show us which rays contribute to this glow. So I'm going to double click on the LPF result. I'm going to draw a rectangle here. And now you can see these rays that were drawn And all these rays are the ones that are passing through our glow. And as I follow these rays back, you can see that they're all essentially coming from the reflection off of this chamfer. So we've effectively now identified that this chamfer is causing this weird little glow. All right, so why don't we try and fix it? I'm going to double click on all the faces, and I'm going to simply hit F to remove them. I'll do the same thing for the circle and our squiggly. Okay, and now I'm going to solve again to see if that fixes our problem. So I'm going to hit compute. Okay, the simulation is completed, and there you go. You'll notice that the glow that we had, the weird bloom, is gone. And so what I've demonstrated here is essentially an ability to rapidly iterate on your design and identify issues both visually and by measuring using the tools available in SPEOS before having to build a prototype. This is obviously very valuable to be able to speed up the design process and get you a better product out to market quicker. I hope you enjoyed today's demo. If you have any questions, please feel to reach out to us, and we'd be happy to give you a lot more details. Thanks for watching.